Hello and welcome to this episode of the Industrial Engineering Notebook. Today's topic is maximizing profit. Obviously, maximizing profit in all cases is going to be complicated, but we're just going to look at a relatively simple example where you can use derivatives to maximize the profit for a widget in your factory. The first thing we're going to do is make a graph. We got $sign on this axis. And this axis we're just going to call the variable x, which is just the number of widgets made. So before you make any widgets, there's going to be some fixed costs. And let's say it's right there. That's your fixed cost, not going to change with the number of widgets you make. And then you're going to have some variable costs. And that's just going to increase linearly like this. This is a perfectly straight line that you're looking at here. So it's just going to linearly increase. That is a tough word to say. The more widgets you make, the more cost you're going to incur because you need more material, more labor, all of that stuff to make more widgets. So this line represents your cost. But you're not just making widgets to incur costs. You're making widgets to make money for yourself and your company. So the other thing we need to consider on this graph is the revenue. And we can model the revenue as a kind of parabola. And remember that revenue is different than profit. Profit is how much money you get in your pocket at the end of the day. Revenue is just how many dollars you make at the outset. So if it costs you $2 to make one widget and then you sell that widget for $5, your revenue would be $5 and your profit would be $3. So here's our cost and here's our revenue. And we want to know how many widgets should we be making? Notice that the answer isn't as many widgets as possible. It's something a little bit less than that. And you might be inclined to say, well, let's make the number of widgets that maximizes our revenue. Let's make this number of widgets. And that's a good first guess, but hold your horses because remember, revenue isn't how much money ends up in your pocket at the end of the day. Revenue is just how much your customer is going to pay you. So that's not quite what we want. Really what we care about is the distance between these two lines. So this distance would be the profit you would make if you made that many widgets, this distance here. But we want this to be bigger, as big as possible, right? You want to make as much profit as possible. And it actually looks like we could make a bigger profit if we made this many widgets, which is less than that. So this would be X star, or the optimal X. Here's the issue though. There's not a nice clean equation for the distance between these two lines that we can plot. I mean, the equation exists, but that we can plot on a graph, not so much. That'd be kind of tough, right? You'd have to measure each little line as you go through here and then make a separate graph, and that'd be really hard. But we don't want to do that, and we have the magic of calculus, so we don't have to. We'll begin by writing an equation for our costs. So total costs, TC, equals our fixed costs plus our variable cost, CV, times X. So this is a big C because that's the dollars. The little c here is dollars per widgets made. So it's a little c. You make a lot of widgets, this term gets bigger. This term stays the same no matter how many widgets you make. The next equation we want to write is total revenue. You might be wondering why we chose a parabola here for revenue. The idea is basically as you start to make more widgets, you can more things and then get more money from your customers. However, at some point you kind of reach a point of diminishing returns. So at this point, maybe you're forcing overtime or you're incurring financial risk because of how often you're using machines, or maybe your machines are starting to break down and you're just making less and less revenue even though you're making more widgets. So that's kind of why we have this parabola shape. And the specific parameters associated with this parabola are kind of just going to depend on the specific situation. So we'll just use some general variables here. We'll say that total revenue equals negative ax squared plus bx. And depending on the situation, you can change the values of a and b, but negative x squared plus bx ensures that you will get a parabola shape, an upside down parabola shape like this. And again, we don't really care about maximizing revenue. We care about maximizing profit. So profit, which I'm going to call big P, equals total revenue minus total cost. And if we plug in TR and TC, we can get an equation for profit. And just like that, we have our equation. So we don't have to try to worry about plotting the distance between these two lines at all these points. We can just write an equation with math instead. And to find the maximum of this function, we need to take the derivative and set it equal to 0. So check out the defining derivatives video for more information on that. And then after we set the derivative equal to 0, we need to ensure that we're finding the maximum of this function. So we need to make sure the second derivative is negative. One step at a time here. First up, I'm just going to rewrite this. It's a little bit more concise. I'm going to write an equation for p prime, or the derivative of p. Check out the derivative rules video for more information on that. Negative 2ax plus b minus cv. Just like that, we got a derivative. Next step to maximizing profit is to set the derivative equal to 0. This is just negative 2ax plus b minus cv equals 0. And then we're just going to solve for x. So negative 2ax equals cv minus b, which gives us x star, or the optimal x, equals b minus cv all over 2a. And before we get too excited, remember we got to check that the second derivative is negative. So p double prime, the derivative of the derivative, we'll have to look back here. These two are constants, so they'll just be 0, and then we're just going to have to take the derivative of this, which is just going to be negative 2a. That x will disappear. P double prime equals negative 2a, which is indeed negative, which means this is not a minimum, it is a maximum. Which means that once we have the parameters for this revenue function, A and B, and we know our variable costs for each widget, we can determine how many widgets we should make in the first place because we know the number of widgets that will maximize profit. If you found this video helpful, give it a like, please. If you want to see more of these, you should let me know by subscribing. If you have questions on this topic or any other engineering topic, put it in the comments.